So it starts with HCl, so this is the same one you modeled. Okay, and then draw an arrow with me so the H moves from here to here. And so this is classified as the acid, and this is classified as the base. Because acids donate, bases accept. And then on the reverse side, you should see the result of it, that this one lost the H+, which is why it became negatively charged, because it lost something positive. And this one gained the H+, and that's why it now has a positive charge. I've mentioned it before, but positive and negatives are very important to the identity of a substance. This is not the same thing if I take away that negative, okay? Now, as we look at acids and bases, so that's the first step of identifying, hey, that's an acid and that's a base. The second step is we then have classifications of acids and bases. We have acids that are considered strong and bases that are considered strong, and then vice versa, there are weak ones as well. So this is a list right here of the 7 strong acids that exist in the world. Anything not on this list is considered a weak acid. By definition, what we mean is it's about the amount that dissociates. Okay? Strong acids react completely. They go all the way to product. And that's what this blank that I forgot to fill in should say. The reaction lies entirely, you could say, to the right or to the products. If it was a weak acid or base, it exists as an equilibrium, where sometimes the acid gives its H away, but other times it holds it. Or I guess I should say, not all of them do. So if we were a strong acid, that means all of you would give up your H. If we were a weak acid, maybe only this table would. And the rest of you would hold on to your H. So that's the difference between strong and weak, is the amount of the H's that actually get donated. Okay, so strong acids are full donors, weak ones are partial donors, depending on how much you get. Okay, now this list right here, we, in a sense, are going to somewhat memorize the strong acids.
Oh, nice.
For now, we're not going to focus on memorizing them, which is why I wrote them over here too for today's lesson, because I just want you to focus on understanding. So on the homework and everything, use your list. One day we'll spend the time to make sure we have them done. Okay? I'm going to do this one with you, and then I'm going to have you try that one for a smiley face. So if I'm writing the equation for technically any acid, we should show that process of giving up an H. So write HClO4. By the way, the middle table identified this, and maybe some others did too. Acids are always in an aqueous solution, always. They're always aqueous, meaning they're always in water. So this one's gonna give up its H to here. So then the thing that gets left over should have a negative charge, and then the thing that was created has a positive charge. Yeah, Jack, then Zach.
One of the acids on the right that we have is a gas.
So I guess I should clarify in the sense of all the strong acids are always aqueous. Weak ones can exist in the room. Sorry, I forgot to clarify that word strong. Thank you for, is that what your question too, Zach? Okay. All right, try the second one for smiley face. It only gives up one H though. So it comes with 2, but it only gives up 1.
Right, but I thought you said it was strong, so it's small.
So it gives up that 1 fully. Does that make sense, the difference, Jonah? Give me a pencil drop when you're done. If your answer matches mine, then you'll get a smiley face. You can check with your neighbors once you're done to see, like, sweet box. Really excited. I'm gonna buy lights. Change color of light. I'm gonna
Wait, what's the?
What? No, it'll be here like next week. So we'll start testing.
Was this a mistake on paper?
Also, there's no O.
Because the only thing that changes between this one is you're sending the row, but this becomes H plus
It
CL.
should have.
It should be H3O. Okay.
You'll actually see in a minute why I accidentally did that.
So
You'll see. But it is technical.
should we write it in?
Okay, if you have this on your paper, HSO4 minus and H3O plus has a sign. Okay. Turn the page and let's look at our list of our strong bases. Our 8, I guess there's 8 strong bases. Okay, once again, the idea of a strong base is that it can completely or always accepts the H's. On the other side, in terms of it dissolving, it just breaks apart 100%. Okay? Now, with the bases, everybody, it's actually easier to memorize them because there's a pattern with the periodic table. So take your finger with me really quick, and I want you to put it on lithium on the periodic table. Put your finger on lithium, everybody. So put your finger on lithium. Lithium, that's your notes. Okay, put your finger on lithium.
Chill out, like it's not that serious.
Okay, mouse close, please. I'm going to read through, and I want you to see based off, so you're on the first one, so lithium hydroxide is our first strong base. I'm going to read the list, and I want you to see if you can see the pattern on the periodic table. Okay, so the next one is sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. Now, there's going to be a little jump here, but we go to calcium hydroxide, strontium hydroxide, and barium hydroxide. So as you can see, they're kind of grouped together on the periodic table. So I think they're a little easier maybe to memorize, but yeah, I would assume francium and radium would both be strong, but they're both so radioactive and like rare that you're never going to work with francium hydroxide. So, okay, questions so far on strong and weak? Okay, now let's talk about when we start bringing these things together. Okay, so when I have a strong acid, or I should say any acid applies to this in this case. One thing we need to recognize throughout this entire unit, if an acid and base are poured together, they will always react, because one wants to give, the other wants to take. Okay? When it's a strong with a strong, they are classified as a neutralization reaction because of what is always made. So right here I have some hydrochloric acid. As you can see, once again, it is aqueous. Bases, fun fact on the other side, they don't have to be aqueous, like this started as a solid. I made it aqueous so it will react better, but bases, unlike strong acids, which are always aqueous. Okay? So if I take a strong acid and a strong base and mix them together, it's known as a neutralization reaction because you always make water is one of the key components. So let's label this here really quick.
Wait, it's NaCl and H2O.
Okay, so this is a strong
What
acid.
teaspoon?
Okay, this is my strong base. The two products it always makes is water and a salt. Reminder that the word salt in chemistry includes anything ionic. In this case, it's actual table salt. But a salt, when I use the term, okay, is any ionic compound.
What are the ionic compounds?
So that's a good reminder. So how do I identify if something's ionic?
If it's
It's brand, yeah, so metal plus non-metals. So what have we created?
We created salt water.
Right?
Okay. Oh. You took it too.
You know, liability, I guess. I'd rather burn myself than you.
Burn.
Okay, now, here's the catch, and we'll talk more about it. Just because it's a neutralization reaction doesn't actually mean it's at a neutral pH. So how do I know this is actually safe to drink?
Test it.
Here?
You get to somebody else.
Because I just died. You already drank it.
Here? I don't know.
What would cause it to not be
Oh, did you measure it out? Exactly.
good? Yeah, the moles have to balance out, right? There has to be the same amount of moles of this to the moles of this, otherwise you could have excess, right? You have leftover HCl still in the flask, which would not be good. Neither would excess of this. So, does that make sense, neutralization? Okay, now once again, when it's not strong and strong, it can still, in a sense, it neutralizes that they react, but you don't create, you'll never be able to create a perfect balance of 7 when it's weak and strong, because the idea that one of them is in equilibrium. Okay, now full disclaimer, don't try this at home, because I didn't either. These were just water to begin with.
Oh.
I played in yes. But for safe, that's why I like.
Can I drink it then?
Yeah, it's just water. It's not very tasty water, but
Not very tasty water?
yes,
You
Ellie.
said balance of 7. What did you?
So we'll get to more of it today, but if you've learned about the pH scale, 7 is the very middle. So 7 means neutral.
Yeah.
But we'll talk more about it if you haven't learned about the pH scale. Okay, let's try this practice problem here, everybody. Okay, eyes up front. I'm going to do the first 3 with you, and then I'll have you try 3 as a table in practice. Okay? So our first objective here is to identify whether something is an acid or a base, classify it as strong or weak, and then if there's a salt present, I want you to label that as well. Okay? So, first thing I do, once again, is look at the full story, and I start by looking at the products. In this case, if water is made, and if the other thing is ionic, so this is a metal with a non-metal, I know by for sure that both of those have to be strong substances, because only strong substances make water and a salt. So I know this is a salt because it's ionic. So now coming over here, I can identify the base, because strong bases always have OH attached to them. So I know this is my strong base, and this is my strong acid. So if your products are water and a salt, you know for sure that they're both strong. Coming to the next one here, in this case, I didn't make water and salt, so I know that one of them could be strong, but they're definitely not both strong, and maybe they're both weak. So now I'm going to track the movement of the H. So this started as HBr, and it became Br minus, and I see that the H moved from here to there. Because notice how now on the other side it's NH4+. Everyone see that movement of the H, okay? Which tells me that this must be my acid, and this must be my base. Questions so far? So now I have to label if they're weak or strong. Strong bases don't have OH, so I know this must be weak.
No, wait. You said strong bases don't have OH?
Sorry. Strong bases always have OH, and so that one must be a weak base because it doesn't have it. Okay? This one for the acids are a little trickier, and so once again right now, I can just check my list. It is a strong acid, so I'll label it as such. Which means, once again, there's no salt present. Okay, third one, coming to the products, there was no water or salt created, so I know they must be weak to some extent, so I'm going to track the H. So the H moved, it looks like, from this substance to that substance. So once again, I see the H being lost because you just have the C2H3O2 with the minus. So this one must be my acid, and I know it's a weak one because it's not on the list. And then water I know is not one of my strong bases. then again. Like, since it has lots of H's. Not entirely, but they're definitely, you could like kind of say like, weak ones often are a lot more complicated formulas than the strong ones. Because like this one does have 2 H's, but it is a strong one. But, so kind of a pattern there, but not like a hard pattern. Good question though. Okay, any other ones? Okay, try the practice off to the side. How I want you to do it is like this, everybody. Put your pencil down for a sec. Eyes on me. Because this makes it a little go faster. So you're going to try the problem, all 3. When you think you've got them, you're going to compare as a table. If you all, once your whole table matches, then raise your hand, and I'll come check you out. Because then I just will check one paper, but I'll know they're all the same. Does that make sense? Okay, ready, set, go. 3 smiley faces up for Brad.
Water the acid.
Yeah. What do you mean? No, you shouldn't read it in the way it's
Yeah, wait, so weak base, weak acid, strong base, strong base, water, so weak acid. Oh, we have to do
H2O water is oh, what is that?
That's all from right now though, so it's your daily for like
Water out of 7.
ready? Okay. Perfect.
What pH is
Smiley faces.
They got a red chunky here. Maybe.
Oh,
How'd you do that? Oh, you just like.
never mind, hold on.
We ready?
Synthetic kiss.
Okay, here we go. We have
Yeah, it's just computer. What are you doing? I'm making tomorrow's class.
Ready?
I was right, mostly. I was mostly right.
Oh, there we go. Oh, yeah, go. Good job. Have to use my hands. Well, we had a great Okay, ready?
I just have a question, but we haven't accepted prices.
I may have it.
But I have a question. Yeah. Or you have it too?
No.
So, in this one, it's kind of hard to tell what the H is actually saying.
It's a little trickier with strong ones. When it's strong with strong. That's why it's like I almost just do products. And then I know the acid that base is always because I agree, it is with a strong, strong, it's a little trickier to see.
Like this one, like gives them NO3. Is wait, is garbage?
Yeah.
Will next, maybe the next time, will actually start writing mathematical equations, which then I think it shows the abilities of the strong ones.
Well, it's on my stronger actions.
Ready? Oh.
Probably.
Oh, look, strong.
Oh yeah.
We call that kiwi. Kiwis.
So I guess just like this
There's
gives
the other outside of this chair.
Well, you don't have to worry about that.
but I want to know how it works.
How it works.
Because it's like
He gets, and then he gets this from the table. Ready?
Or you'd have to be like Jonah size. Because that goes there. No, because
well, this is not ionic.
That's what it says. So like, no, almost. Yeah. No, not quite. Yes, no. Yes, no. Yes. Then go right here.
I changed the slide, but that writing was funny. Okay. The first thing, there's a salt somewhere.
I want to know why it happens.
And then, on this first one, so what's the definition? What do you ask? Good. Have 3
Oh, that's sick.
Okay, I think I checked everybody, right?
I'm pretty sure I thought they were called jams.
Okay, I want to clarify just one thing as we go to the next slide.
That wasn't funny.
So what did we just identify with water in this problem? Yes, so water can be an acid and it can be a base. Now we want to clarify here that, all right, side talking should stop. Standing alone, water is not a base, water is not an acid, but it has the ability to react and behave depending on what it's with, okay? All right, now the next thing we're going to look at here is the things that are being created, okay? So when an acid gives up its proton or its hydrogen, the thing that it turns into, we call it its conjugate pair. The thing that was made after it changed. Same thing, the base has a conjugate pair. When they are a weak substance, their conjugate pair becomes the opposite of what they were. So an acid's pair becomes a conjugate base, and a base's pair becomes a conjugate acid, because it has the ability to go back the other way, because weak things go back and forth. Right? They're in an equilibrium state. If it's a strong substance, it still has a pair because it created something, but we call that thing not so much, it's not really an acid or a base, we call it just a neutral ion. Okay, so if you identify that it is a strong acid, the thing you pair it up with, you don't call its conjugate base, you could call it one of two things. You could just say it's a neutral ion, or you could say it's its neutral conjugate, right? Because it is still kind of linked to it. All right. I know those are quite a few blinks. I'll give you a second, and then we'll try 2 problems together, and then I'll have you try some ones on your way in. That's one thing I've tried to improve in this unit is a lot more of I do a problem, now you guys try it out. I do a problem to hopefully help us understand a little bit better. And maybe catch anything you're not understanding. Okay, let's try these 2 problems together. So similar to before, let's start by identifying the acid and the base. Okay, So if I notice here, I see that H is traveling from this substance to this substance, which makes this substance my acid. The thing it turned into was NO2, so I'm going to match it up with its pair, because it was this and now it's that. And this we call its conjugate base. So the thing that acid turns into is the conjugate base. This one is the base, and we know it's weak because water is not one of the strong. I guess I should have added on here, we know this is one of our weak acids. It's not part of our 7 strong. The weak base is turning into this, so this would be classified as our conjugate acid. Because it has the potential to now give up its H if you read the reaction going the other way. Questions on that? Okay, let's try one more. So looking here, once again, track the H movement. So it's NH3 on this side. I pair it up with what it turned into. It became NH4, so the H moved from here to there. So this one is my weak acid. And this one would be my weak base. And then the conjugate pair is going to be the conjugate acid. And then the water, this would be my conjugate base. On your homework and the next practice problem, if you want to abbreviate these words into like WA, WB, CD, CA, I'm okay with that. On the actual AP test, I would like write out the words.
Could you write like con base?
On the real test, I just make it very clear. But for this sake, you can read it. Okay, try these 2 problems, identifying pretty much the reactants and the products. Everything should be labeled here, and then we'll check it for some smiley faces, okay? So this one I won't come around individually and check. I'll come around and look, but we'll check it on the board in 3 minutes.
So I got weak acid, weak base, conjugate acid, conjugate base. I got weak acid, weak base, conjugate base.
I think that's a strong acid.
This house is
Yeah.
Oh, this one does the weird switcheroo.
It does.
wow.
These wings.
Zip by his whole house.
I like them better with arms. I like them better with arms, yeah. So the furthest right.
That's one of the strong acid.
Yeah.
Check the table once they're done.
It's just
Make them like 4-legged.
so annoying.
You are a silly man, Alex. Hey!
I'm sorry.
Oh,
Not for
I was fidgeting. That's how I focus. Could always go back to our What? There's no H. There's no H. Is there an H2O? Headache.
Because it doesn't really go back.
For number 1, right?
Yeah.
oh, I did it again.
You did bad.
It's like basic.
Yeah, probably.
I understand what you're saying. But it's
So, I don't think I've ever.
You're gonna actually do that on the AP test. There's no
Hey, how's it going?
Hey, how are you?
There's someone that.
I know.
That's
I'm
good.
just trying to keep their structure together.
I actually.
I hope you're having a good day.
Oh, what's up, Ian? Like, I used
up,
a
Ian?
regular guitar and then I brought it down.
If you did it
Like it on our
one, then you kind of don't.
What is the most recent project?
Okay, if you're done, I'm gonna put the answer on the board. If you're not done, don't look up yet. Finish up and then check.
How did you bring it down?
I just recorded it and then
She just borrowed some people's blogs. It's awesome.
wow.
Have a smiley face if your labels match mine.
Yes.
Oh, no. Wait, our papers are reversed from that. That's what I'm confused. So like the CHO is on the left side and the H3O is on the right side. But it's the same. It's not? Really?
That's the same equation. That's the same equation.
Oh, I was looking at the wrong thing.
Oh, okay.
I'm so. That's my bad. That's my bad. I'm like,
Okay, are we okay?
I was looking at the top.
Where did you took a This makes sense. So what did this just
Yeah. You might have like accidentally like plugged up.
turn into that? And space is
TAS.
Or it's a 411.
Oh,
TAS.
you didn't pay attention, you just did the graph. Okay, check the second one here.
I don't know where he is. I don't know who this task guy is.
Okay, check the second one.
You did not get that. You did not get this.
Oh wait, because it's strong at.
So yeah, the trickiest one where I get people is they forget that if it's strong, it's technically it's still its pair, but you don't call it an acid base. It's just its the neutral ion or the neutral proton. Okay, questions on identifying these different things. Okay, the next part of our lesson is now we're going to get into introducing you at least into the mathematical side with acids and bases of classifying them. So let's do this really quick. Everybody stand up. I'll give you a 1 minute stretch break before we transition to the next thing. Stand up, stretch.
Let's go away.
What do you mean?
He has so many smiles. He's not really cheap. He has like a whole
Because it gets you loose.
Go ahead and catch the cheater.
I'm just naturally flexible.
How's it going over here?
What did you like?
Okay, have a seat, everybody. Thank you. We'll save like, so in like 10 minutes or like, we'll save 5 minutes. Thank you, I totally forgot. I can give you. Okay, eyes up front here, everybody. Eyes up front. Side talking should end. Lights are green, my turn. Gavin, can you turn your body this way? Thank you. Okay, so our next thing here is learning about kind of the lab side of identifying acids and bases. So we already talked about, so you kind of learned the symbolic side of like molecularly, right? If there's symbols, what's going on. This is how it's labeled in the lab. It actually stems from this, the pH scale is a scale that separates acids and bases by numbers. It was developed developed based off of water. Water does actually very interesting reaction with itself. Because it can behave as a base, and an acid, it can react together. So you can take a water molecule and react it with another water molecule and make, this is the hydroxide ion. Kind of a good one to know by name because we use it a lot with acids and bases. And this is called the hydronium ion. It's the H3O plus. Okay? Yes, Bryson?
Wait, so you're reacting neutral water with neutral water?
Yeah.
And it just does that?
So all you have water on your desk right now,
You do?
it's happening right before your eyes. The water's reacting with water because they're both there. Right? So, are we drinking this?
Sure, I don't know.
If you were to drink just pure hydronium.
Isn't the reverse reaction happening?
Maybe
This becoming those. Nope, so it's the water molecules react with other molecules to become this. Here's the catch though. You are drinking this,
I don't see it.
but it's at equilibrium
So, we whatever.
and it's extremely reactive.
Oh, okay.
So most of what's in your bottle is H2O. But a very, very, very small extent, 2 out of every billion, are turning into hydronium and hydroxide. Okay? That your esophagus would not. Would not be good.
It's like you're That's not bad.
So with this idea here, everybody, eyes back up front. Water is what they use as kind of the standard of the scale as the middle neutral ground. Okay? Now, one note as we keep moving forward, and I've kind of already hinted towards it because it's just my natural tendency, so this is part of the error. Chemists often simplify H3O plus in an equation, in a picture, and instead of writing all this or showing all this, they simply just show H plus.
Oh man.
It's not just H plus, it's always going to be hydronium, but for simplicity's sake or laziness sake, that's how chemists are, they just write H plus. So keep in mind, we're going to start seeing that being interchangeable here in a second. This is technically never going to exist. It's always going to bond with water and become H3O plus. It's never just going to float by itself. But for simplicity, we write it that way. So this equilibrium, as I mentioned, is extremely reactant favored. Its K value is 1 times 10 to the negative 14. Very, very much reactant favored. Now, because it's a special K, they gave it its own subscript of a W for water. So it's known as KW, but it's the same Ks as we just learned about in Unit 7. So what's the setup for any equilibrium K? Products over reactants. So my equation's up top. Now what do we exclude from equilibriums? Solids and liquids. So the waters we don't include in the expression because they're liquid. So KW equals OH minus and H3O plus. Or as I just mentioned, it's the same as OH minus and H plus, because we're saying those two represent the same. With this base standard, when those two things are completely equal, as they are in distilled water at 25 degrees, that is called a neutral solution. When you start getting more H's than you do OH's, that's when it becomes acidic. Keep in mind that they're always both there. It's just a matter of getting more than the other, and then the other side would be basic. So if I go into a lab and I measure how much H plus is in a solution, I can know, like, oh, this is an acidic solution. From that, scientists said, well, we can do that, but often the concentration values of these things are very, very small. It's like 1 times 10 to the negative 5th, or 1 times 10 to the negative 12th. And those numbers, like scientific notation numbers, are like trickier to interpret sometimes by just quickly looking at them. And so that's where the pH scale was developed. It was a way to change concentration into a 1 through 14 or 0 through 14 scale. So it was much easier to interpret. So the pH scale, once again, has no units because it's simply a scale, right? It was just developed to show acidic and basic solutions based on those concentration measurements. So the way it was calculated is it's a log-based scale, so it's the negative log of the H+.
Oh, brother.
Now take a breath, everybody. It's fine.
log in math.
Okay, if you have not learned logs yet in math, it's fine. For now, just know it's a button on your calculator you're gonna push. Okay? If you want to know how it works, that button, I can have a side conversation with you. But we're just going to use this mathematical button. Okay? Now, this one here, everybody, make a note of this. This one's on your formula sheet. This one's not. I don't know.
What is 10?
You can write on your formula sheet. You won't get it till like the moment before, but.
What is 10?
So the opposite of a log is 10 to the power of x, or in this case p.
10 to the negative.
So if you understand how the log works, it's the inverse of it. It's also on a lot of calculators. It is nice. The one that's not on your formula sheet is often right above the log button. So if that kind of helps. Like my log button's here, and 10 to the something is the second power right above it. So it's kind of, you can remember that's just the inverse. Okay? Okay, back table. We're having way too much side talking. Okay, we gotta figure it out or we're gonna move on. Okay. All right. So with these two equations, once again, a few things we need to recognize here. It's measuring, it's the same thing as before. It's just changing the number into a 0 through 14 number compared to 1 times 10 to the negative whatever. So if those two things are equal, what type of solution do I have? Neutral. It's neutral, and it ends at the pH falls right at 7. So when pH equals 7, it's a perfectly neutral solution. Technically, a pH of 7.1 has become very, very slightly basic, right? Only 7.0 is perfectly neutral. It's still pretty neutral, but once again, only right on the dot, okay? If there's more H+, what type of solution has it become? Acidic, and because of how the log function works and that we're taking the negative log, you get a flip. And so when the pH will be less than 7 when it's acidic. So less than 7 is acidic, and then when there's more OH, pH will be greater than 7, and then of course it's basic. The other thing, if you're not familiar with the log function, is it's a base 10 relationship. So the difference between the pH of 1 and a pH of 2 is 10 times the strength. So don't be deceived like, oh, it's only a difference of 1. No, there's a big difference because it's base 10. To give you an example, we'll talk more about, right, your blood has a very specific pH range it needs to be in. And if it goes even just 0.1 out of that range, you could die. You go into blood acidosis. Or the other direction. That's the acid side. I can't remember if your blood gets too. I can't remember what it is. It's like alkaline. They use alkaline as like another fancy word for base. Yeah. Yeah.
So just to clarify, so whenever we see H+, should we always assume that it's H3O+?
Yes. Yeah. Okay, here's a little picture at the bottom, just to put it on the scale.
10 times worth of pH.
Okay, add this on for me here. Remember, if it's an acid, what do I have more of floating around? Right, so there's more H plus if it's an acid. And if it's a base, alkali is like a fancy word for bases as well. We'll typically use bases, it's just the picture I found. What is there more of if it's a base? Yeah. And then right at neutral, those two things equal each other. Yeah, right.
Are they called alkali metals because they're like the strong bases? Or like they're like used in the strong bases, I guess?
Because the alkali family. Yeah, so that's where like alkali comes from, is because the strong bases come from the alkali earth and the alkali metals. So yeah, that's why the alkaline, because the strong bases are all alkali type metals. So yeah, it's a good connection. Okay, any other questions? We're gonna stop there. Okay, so there is one small change to our homework assignment tonight, because I didn't want to rush it, and I didn't rush it with B6 either. So front side, and I'll even put this as a label, the front side of 8.1 is your homework. So it's conjugate acid, bases, neutral, all those things. The back side we'll do next time.
What if we do the backside? Extra credit?
Step ahead. No. But we'll do it next time.
I mean, but you are the side.
So that's one common misconception. A lot of times people always think acids are more dangerous. They're both just as dangerous. They just do different things to you.
Wait,
What if you drink stomach acid?
you would get more stomach
Well,
acid.
so you know when you like, sorry to be like,
throw up.
when you throw up and you like, it burns? That's like, so imagine that going down instead of up. Yeah. And then in a sense,